Welcome to the 8th lecture of this course on solid mechanics. And today we will be talking about planes on which the shear component of stresses are maximum, or we will be talking about maximum shear stress. So there are two topics today actually. One is maximum shear stress, the other is maximum shear plane. And we will be covering both of these in today's lecture. Now for today's lecture, the concept is very similar to what we covered in lecture 6, which was basically maximum principal stress. So in that lecture, we maximize the normal component of stresses. Today we are going to maximize the shear component of the stresses. So let me share the screen and start with the lecture. Okay, so I hope my screen is visible to everyone. So let us start. So what is the objective for today's lecture? So let me first write down the objective. So there are two objectives actually. One objective is find the maximum shear component. So that is objective number 1. What is objective 2? Objective 2 is on which plane the maximum shear stress acts. So we want to find out the plane as well as the shear stress itself. And how are we going to do it? We are going to do it by following the exact same procedure that we followed for determining the maximum normal stress, which was also known as the principal stress. So let me go to the white screen and start with the derivation. So suppose we have a arbitrary body, something like this. This is arbitrary body, and say there are some forces that are acting on this body. And then we have a boundary condition. So we are going to take a section here. And so if I taking section, what do I get? We get something like this. And then this is the cut section that where we have cut. And then this is my normal direction. The traction may not act in a normal direction. So in a generalized scenario, this is the traction that is acting on here. And then if I change the color, let me change the color actually. So let me go to something called like green. So then this is the sigma n will act in this direction. We can also call it sigma nn actually. And this is the tau n. So this is what we will get. Now, what is sigma n? So sigma n is projection of Tn in the n direction. So this is something we know. So sigma n, instead of writing sigma n, we can write Tn dot n, right? Now there is another way of drawing this, these three stress and traction components. And what is that way? So there is another way of drawing it. So instead of drawing it like this, so what we have originally drawn it is something like this, right? This is sigma n. This is Tn, and then something like this is your tau n. So instead of drawing like this, equivalently we can draw it something like this. So this is Tn, this is tau n, and then this is my sigma n. So this angle is the 90-degree. So from this triangle, if we use, so using Pythagoras theorem, what do we have? We have tau n square is equal to sigma n square plus Tn square. Now, you need to be very careful here when you are writing this, because what is sigma n? Sigma n, comma tau n, these are not the stress tensor, these are stress components, right? Or components of the stress. One in the normal direction, the other in the uh, parallel direction, parallel to the plane. And then this Tn is traction vector. So we have some components of stress and a vector. So clearly we cannot add component of a stress to a vector. So what we do instead, or what we need to do to be mathematically precise, is take the magnitude of the vector. So when I write this one, this is nothing but magnitude of vector Tn. So this is something you need to be very careful about, that this is magnitude of the vector and not the vector itself. So then what we can do is sigma n from here is Tn times n, or Tn dot n. So we are going to substitute it. Okay, there is something wrong that I can see. So this is the correct expression, right? So the minus sign will be there. So now Tn square is magnitude of Tna. We have Tn, so let us keep it as it is, square, minus we have sigma n, which is Tn dot n square. So this is what we have until this point. Now there is one question that may come into your mind. Remember that when we were drawing the cube, there were one normal component, say sigma xx, and there were two shear components, right? Tau yx and tau yz, zx. So there were two shear components. But in this plane, or on this plane, I have shown only one shear component. So this tau n is actually the resulting shear. So this is not the shear components along x or y direction, but it is the resultant of the two shear components. This is resulting shear actually. Right? So this is something you should be very clear about. You should not confuse that, okay, in this case we have only one component. No, this is the resultant of the two components. Okay. So let me make some space and proceed with the derivation. So this I don't need. Actually, I don't need anything apart from the one in the box. So I'm going to delete everything except the one in the box. That is the only thing that I will need for the derivation from this point onwards. Everything else is a redundant. Right. So let me clear it up. Okay. So I have cleared it now, almost. This portion also I don't need. So yes, so this is what we have, right? And what we are going to do with this, that is the question we need to answer. So let us see. So what we are going to do is, first there is Tn. So what is magnitude of Tn, or magnitude of any vector for the matter of fact? Magnitude of any vector is nothing but the the sum of the square of its components and then square root, right? So this is what Tn, magnitude of Tn means. This is coming from, if you are getting confused, it's very simple actually. So this is A, then here we have A1, A2, A3. So in the first lecture itself we decided or we discussed that magnitude of A is square root of A1 square plus A2 square plus A3 square. So this is what the magnitude is. Now we will do one thing here. That is, let us take principal planes as our reference plane. So instead of taking an arbitrary plane, we are going to take the principal plane as our reference plane. What will happen with this assumption? What n1, n2, n3 will now be computed with respect to the principal planes, right? So N1, N2 and N3 will now be computed with respect to the principal planes because we have taken principal plane as our reference plane. There is one more thing that will happen, and that is our sigma matrix is now very simplified. Our sigma matrix, how does it look? We only have the diagonal terms, and the diagonal terms are the principal stresses, and everything else is going to be 0. So this is what we are working with now, right? Now we have this Tn here. So if we use, so let me write it here, using Cauchy's theorem. So this name, probably I did not use it earlier, or probably I did use it, but this Cauchy's theorem, what is the Cauchy's theorem? Cauchy's theorem tells you that Tn is equal to sigma n. So if I write it in matrix form, what do I get? So Tn is nothing but Tn1, Tn2, Tn3, right? And this will be equal to sigma 1 n1, sigma 2 n2, sigma 3 n3, right? And therefore magnitude of Tn square, so I'm writing the square term also, will become sigma 1 square n1 square plus sigma 2 square n2 square plus sigma 3 square n3 square, right? So that is what we are working with now. What will happen with the second term? The term that you see here, Tn dot n. So Tn dot n, and there is a square, the square we should not forget about, will be, so Tn is sigma 1, sigma times n. And when you do sigma times n, what do you get? Sigma times n you will get, or sigma, I mean, so Tn is, let me write it like this, sigma times n dot n, and then there is a square. And when you write it in an expanded form, you will get sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square, and there is a square also. This square you should not forget. So what we did was we find out these two expressions which were there in the actual expression. So now we are going to substitute equation 1 and equation 2 into equation A. But first let me again make some space. And today we are going to use the same screen because we have to refer to the what have been derived earlier again and again. So let me make some space. So these things you don't need anymore. So yes, we are. Right, and then let us substitute 1 and 2 into A. So what do we get? Tau n square is now equal to, so there is sigma 1 square n1 square, sigma 2 square n2 square, and sigma 3 square n3 square. So if I write it as a summation, it is sigma I square ni square. So this is what magnitude of Tn square is, minus what we have is sigma 1 n1 square, sigma 2 n2 square, sigma 3 n3 square. So we can write it as summation over I, sigma I ni square, and there is a square here. So don't forget the square. So this is the expression for shear stress on an arbitrary plane n. And when I say n, you should always remember that this n, the direction cosines, are with respect to the principal planes. Okay, that is something you should always remember. And what is our objective? Maximize it or minimize it. So our objective is to either maximize or minimize the shear stress the shear component, right? That is what our objective is. So we are going to do it as before, but remember that n1, n2, n3 are the direction cosine. So we have these properties of direction cosine as well, which is n1 square plus n2 square plus n3 square is equal to 1. And this will give you actually, if you write it as before, it will be ni minus 1 sum over I, right? So now this is your constraint. So we have an objective function that we want to maximize, and we have a constraint also. So basically we are solving a constraint optimization problem. We are solving a constraint optimization problem, right? That is what we are solving. Now, since we are solving a constraint optimization problem, we will use the concept of Lagrange multiplier. You remember Lagrange multiplier? We used it during the principal stress derivation, and we are going to use it again. So let me clear this space up again, and then we will proceed with the derivation. So we are going to use Lagrange multiplier. And what do we do using Lagrange multiplier? Do you remember? We form an effective objective function. So what is our effective objective function? Let us say it is f, and f is first the actual objective function. So I sigma I square in I square minus summation I sigma I in I square, right? And then we have so this is the actual objective function, make no mistake about it. And then we have our Lagrange multiplier, and what we have our constraint, right? So this is now my effective objective function, and this is what I want to minimize or maximize. So what am I going to do? I am going to take derivative with respect to the direction cosine, an arbitrary direction cosine k, where k can take the value 1, 2, and 3. So let us see how it looks. So sigma I is not a function of ni. So it will be as it is. It will act as a constant. And then there is ni. So for this first term, what do we have? 2 summation I sigma I square is ni, and then we have del ni del nk. So I have a question for you, and the question is, what is this del ni by del nk? This is something we discussed while deriving the principal stresses. So you think about it. I will come back to it after I write the expression. So you see, I have missed the square here. There is a square term. So now for the second term, so it is 2 summation I sigma I in I square, right? So this is first, and then derivative of what was inside the bracket. So that will give me 2 summation I sigma I in I del ni by del nk. So check very carefully whether this is plain chain rule, but still you check carefully and tell me whether this is clear to you or not, because this is very important. This is what will govern the final result. So be very careful and check it that you understand it or not. I'm repeating myself. So there is this summation I sigma I ni square whole square. So first we take the whole square, and that becomes 2 times what was inside the bracket, right? And then we take derivative of what was inside the bracket. So that becomes 2 again, summation sigma is not a function of n, and then there is 2ni, which becomes, there is ni square, which becomes 2ni, and then the derivative of ni with respect to nk, which is del ni by del nk. So that is what we are getting here. And then there is a third term lambda, which is constant, and then we have ni dot ni is ni square. So we have 2 summation I ni del ni by del nk, and one is constant, that will become 0. So now we have this term del ni by del nk, and if you recall, we discussed it in our previous lecture, the principal stress lecture. Del ni by del nk is delta ik, right? Well, this is the Kronecker delta. Kronecker delta. So we are going to use this, and that will reduce the expression to summation I sigma I square in I delta ik minus, in the bracket it will be as it is, no changes, sigma I in I square, and then there is this 2 summation I sigma I in I delta ik plus lambda 2 summation I in I delta ik. Now again, this term delta ik here will only yield non-zero value when I is equal to k. For all the cases, this will become 0. And if this becomes 0, the terms vanishes. So we will only get a non-zero value when I is equal to k. So what we can do is we can remove the summation and substitute I with k. So that will give us sigma k square in k, and delta kk is 1. So we need not write it. This will be as it is. There is no such thing as delta ik or something like that. So this will not change. Now here again, this delta ik will only give non-zero value if I is equal to k. So we remove the summation and substitute I with k. And delta kk is 1. And then there is this lambda to remove this summation and make it nk. And this is equal to 0. So let me change the color again. I will use green. So this is going to be very important. This is what we will use. So this is the only thing that we need from this point onwards, and everything else I'm going to delete or erase so as to make space again. So except the one marked in green, I'm going to delete everything. So everything. And then what we will do after we delete everything, what I will do is I will substitute k equal to 1, 2, and 3, and then see what we can do with it. One spoiler I'm giving you. The spoiler is that you will not get a single solution. You will get more than one solution from this expression. You will get unique solutions, no doubt about that. But it will not be one unique solution. It will be more than one unique solution. So that is what we are going to get from this. And so that is what makes this interesting. Make this interesting, that we have more than one solution that we are getting. In any case, let me delete it. I'm almost done. And then we will proceed. So I think we can ignore these dots that are remaining. When we are using so many dots, it's quite natural for miss one or two. So yeah, we are done deleting. And now what we are going to do is we are going to write this expression for k equal to 1, k equal to 2, and k equal to 3. So this holds for k equal to 1 to 3. So first let us take k to be equal to 1, and what will I have? So first let us do one thing. There is this 2 which I can cancel out, right? And there is this nk in all the expression which I can take outside. So for k equal to 1, it will be n1 sigma 1 square minus this 2 is here. So let me write it like this: 2 sigma 1 summation I sigma I ni square, and then we have the last term which is just lambda, right? So this is my equation 1. Next I'm going to take k equal to 2, and that will give me into sigma 2 square minus 2 sigma 2 summation I sigma I ni square plus lambda is equal to 0. Then I'm going to take k equal to 3, and this is going to give me n3 sigma 3 square minus 2 sigma 3 summation I sigma I ni square plus lambda is equal to 0. So these are my three equations, and the goal is to solve these three equations, solve these three to compute n1, n2, n3. So that is the goal. Don't lose focus of the goal. Always remember what the goal is. So now, if I substitute n1 is equal to n2 is equal to n3 equal to 0, all the equations are satisfied, right? All the equations are satisfied. However, this is not a direction cosine, because n1 square plus n2 square plus n3 square will also be 0, which is not equal to 1, which implies n1 is equal to n2 is equal to n3 equal to 0 are not the direction cosine. So that is not going to work. So let us do some trick. What we will do is we will take this n1 to be equal to 0 from the first equation. From the second equation, let us take this part to be equal to 0. And from the third equation, we will also take this part to be equal to 0. So we are taking the first from the first equation n1 to be equal to 0, and from the second and third equation we are taking the other two terms to be equal to 0. So let us see what will happen. So from the first equation we already have some result. So our job again is to compute n1, n2 and n3. And from the first equation, we already have a result which is n1 is equal to 0. So this is one of the result, or 1/3 of the result, if I'm more specific. And what we get from the second and the third part. So n2 is not equal to 0. We are going to remove n2. And what we get is sigma 2 square minus 2 sigma 2. Then we are going to write the summation. The first term of the summation is sigma 1 n1 square, and n1 is equal to 0. So that term will vanish. So we have sigma 2 n2 square plus sigma 3 n3 square, right? Plus lambda is equal to 0. This is my equation 1 now. From the last equation, what do we have? Sigma 3 square minus 2 sigma 3. Inside the bracket, the same thing is there because n1 is 0. Sigma 3 n3 square plus lambda is equal to 0. Now lambda is something unknown, so we want to eliminate lambda. For eliminating lambda, what we do is we carry out this. We subtract 2 from 1. And what will it give us? The first term will be sigma 2 square minus sigma 3 square, right? And then if I take minus 2 common, this term inside the bracket is same, so I can write it as it is. And then what do I have? Sigma 2 minus sigma 3. And lambda will cancel out. So this is what I get. Check carefully. This is simple algebra. You should be able to understand it. I have only taken the common part outside and then the rest of it is simple. So now there is sigma 2 minus sigma 2 square minus sigma 3 square. A square minus b square. So if you use the formula, this will become a plus b and a minus b. And then for the second part, I am writing the sigma 2 minus sigma 3 before the other component plus sigma 3 in 3 square, and this is equal to 0. Now generally sigma 2 and sigma 3, these are two principal stresses, and generally the principal stresses are different. So generally in a general situation, sigma 2 will not be equal to sigma 3. So we can cancel this term out. And what do we have once we cancel this out? Sigma 2 plus sigma 3 is equal to 2 sigma 2 n2 square plus 2 sigma 3 n3 square, right? So now this is actually the only thing we need again. So I'm going to retain only this part and delete everything else. So this is the only thing we need. So I'm going to delete everything else. Erase. So let us delete everything else and then we will see what result we are getting. N1, remember, so this N1 I'm going to retain because N1 is equal to 0 is one of the solutions. So that I will retain, but not the other part. So basically the two boxes, one box in red will be retained, one box in green will be retained, and that is it. Everything else will be deleted. Right, so let me delete it and then we will continue. There should be some easier way to delete actually. This is too tedious. So almost done. Just bear with me a little while more, and then we will have our solution. So yes, it's done, right? So let us now look at the solution. So what I'm going to do is I'm going to rearrange it. So let us see sigma 2. If I take it common, I have 1 minus 2 n2 square. Similarly, if I take sigma 3 to be common, I have 1 minus 2 n3 square. And this is equal to 0. Right? Now, again, sigma 2 and sigma 3 are the principal stresses. And generally, in a general sense circumstances, sigma 2 comma sigma 3 will not be equal to 0. And there are some arbitrary value. So therefore, for this equation, for equation 1 to be 0, we must have actually 1 minus 2 n2 square is equal to 0 and 1 minus 2 n3 square is equal to 0. So both of these terms would be equal to 0. Only then you will get a 0 on the right hand side, because sigma 2 and sigma 3 are some arbitrary value. Now from this one, what do you get? N2 square is equal to 1 by 2. So N2 is plus minus 1 by root 2. And from this, you get the same result. N3 square is equal to 1 by 2. Therefore, N3 is equal to plus minus 1 by square root of 2. So how many results do we have here? We have 4 results. So there can be a permutation combination of N2 and N3. For example, 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2, minus 1 by root 2, 1 by root 2, minus 1 by root 2, minus 1 by root 2. So 4 results. We have 4 results here. Now we started our assumption or our derivation with the assumption that N1 is equal to 0. But we can also take N2 to be 0 and N3 to be 0. And that each of those assumptions will give us 4 results each. So in total there will be 12 set of results. There are 12 planes on which the shear component is maximized. And what are those planes? N1 is equal to 0, N2 is equal to plus minus 1 by root 2, N3 is equal to plus minus 1 by root 2. So this is 4 results. Then your N1 can be plus minus 1 by root 2, N2 is equal to 0, N3 is equal to plus minus 1 by root 2. Another 4 set of results. We now have 8 set of results. And then now we have the last set. N1 is plus minus 1 by root 2. N2 is plus minus 1 by root 2. And N3 is equal to 0. So this is now my third set. So in total, there are 12 planes. So there is no unique solution. Sorry, there is no single solution. There are 12 solutions, each of which is unique. So this is the result. So these are the planes on which, so there are 12 maximum shear planes. Right? Now we also want to find out what is the shear component on those planes, right? That is also what we want to find out. So let us see if we can find out that. So let us take one arbitrary value, right? N1 is equal to 0, N2 is equal to plus minus 1 by root 2, and N3 is equal to plus minus 1 by root 2. Now what was tau n square? It was magnitude of the traction vector minus sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square, its whole square, right? Now when you write it, it was sigma 1 square n1 square plus sigma 2 square n2 square plus sigma 3 square n3 square minus sigma 1 n1 square sigma 2 n2 square plus sigma 3 n3 square whole square. Now n1 is equal to 0. So this will vanish. This will vanish. So what do we have now? We have sigma 2 square. Okay, now n2 is 1 by root 2. So n2 square is by 2 plus sigma 3 square by 2 minus sigma 2 by 2 plus sigma 3 by 2 whole square. Right? Now, how can we write it? is a square plus b square. So you can actually simplify it as, let us do it, sigma 2 square by 2 plus sigma 3 square by 2 minus, we have the square now, right? So it is sigma 2 square by 4 minus sigma 3 square by 4 minus 2ab. So it will be sigma 2 sigma 3 by 2. And then you can take the sigma 2 together, and that will give you sigma 2 square by 4 plus sigma 3 square by 4 minus sigma 2 sigma 3 by 2. And this is nothing but sigma 2 minus sigma 3 by 2 whole square. And therefore, tau n is sigma 2 minus sigma 3 by 2. And this is corresponding to the case where n1 is equal to 0. Now, just from intuition, you can say when n2 will be equal to 0, tau n will be sigma 1 minus sigma 3 by 2. And when n3 equal to 0, tau n will be sigma 1 minus sigma 2 by 2. So these are the results of the maximum shear stresses. Now you remember that on the maximum normal stress or principal stress plane, the shear components were 0. So let us now verify whether the shear components are 0 on the maximum shear stress plane or not. So what is the normal stress component? Sigma n. It is already written here, right? This one. So it is sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square. N1 is equal to 0. This will vanish. So what do we have? We have sigma 2 by 2 plus sigma 3 by 2. So sigma 2 by sigma plus sigma 3 by 2. So the observation is that normal stress is not 0 or may not be 0. Let me make it may not be 0 on maximum shear plane. This is not like the maximum normal stress plane or the principal stress plane when the shear components are 0. The plane on which the shear components are maximized, the normal components exist. The normal component is generally not equal to 0. It will become equal to 0 if and only if sigma 2 is equal to minus sigma 3 or sigma 1 is equal to minus sigma 2. So this is what we discussed just now. And now what are the angles? 0, 1 by root 2, 1 by root 2. So 1 by root 2 is cos theta. So theta is 45 degrees. So we can say that the maximum shear plane makes equal angle with the two axes, and that is 45 degree, and is perpendicular to the third axis, right? So if I have to draw it, it will look something like this. So this is one of the plane actually. So this is my x, this is my y, and this is my z. And what you are seeing in the red is the original state of stress. So, and this is, remember, is the principal state of stress. And then we wrote, what is the maximum shear plane? You see, what we have done is we have rotated it about the z-axis. So in the rotated plane, if you look into here, you see sigma 3 is like this. So basically it is n1 and n2 is equal to 1 by root 2 and n3 is 0 because it is at a 90 degree angle. And similarly for sigma nn on this plane is sigma 1 plus sigma 2 by 2, I just showed you, and tau is sigma 1 minus sigma 2 by 2. And same thing on this plane. On the top plane, there exists no shear component because that is a principal plane. Now your homework is to, this is only one. I said there are 12 combinations like this. I've only shown you for one combination. Your homework is to draw for the 11 other combinations. So that is your homework. So I will stop here, and in the next class we will talk about something new. We will see that instead of doing all these maths, how can we do the same thing, at least in some of the cases, by using graphical method, and that is known as mode certain, and that is what we will be discussing in our next lecture. So I will stop here, and we will meet again in our next lecture. So thank you.